You might want 2 banana smoothies ready for this one. We're talking about how the Neuralink threads are built, so get ready for photolithography and electron beam evaporation. This is part 3 of a series of posts explaining the Neuralink white paper from 2019. I'm not going to recap anything from the first or second video. This one is all about answering the question of how they build their threads. In this video, you will learn about microfabrication techniques, and what better place to start than photolithography. Photolithography is Greek for writing on stone with light. Etching designs into substrates with light templates is a common technique in small-scale electronics manufacturing, where the patterns that are carved require levels of precision that are measured in the scale of hundreds or even dozens of atoms in width, as in computer chip manufacturing, where the functional components can be 10 to 50 nanometers across. To give a sense of scale, a silicon atom has a covalent radius of about 0.11 nanometers. The microfabrication of Neuralink threads follows a similar playbook to computer chip design and manufacturing. The big picture is this. You start with a thin disk of silicon lattice as a base layer. On top of this disk, another layer of materials can be stacked that is able to be carved with light and make a template. Into or against this template, another layer of materials can be deposited. This process can be repeated over and over again, precisely stacking templated layers of materials until the microfabricated device is finished and can then be removed from the silicon disk. The two major materials in Neuralink's threads are the dielectric insulator, polyamide, and the conductor, gold. These two materials can't just be randomly mixed together in a pot like a soup. They have to follow a strict spatial template in order to function properly as a bundle of small wires with electrode contacts at the end where they can exchange current with the tissue. The Neuralink white paper doesn't go into the exact specifics of step-by-step how they microfabricate the threads, but by looking at other academic papers, especially one they cite from a collaborator for the prototype, we can infer the kinds of processes that they use, and this actually is really insightful to understand. So we'll look at 2 examples. The first one is from a relatively simple brain-machine interface that just goes on top of the cortex, and the second is a more complex design from one of Neuralink's early academic collaborators. Although the designs are not exactly the same as the Neuralink threads covered in the paper, they show the kinds of techniques that are used for microfabrication of this kind of thread-based electrode cluster. This image is from a 2019 paper which shows step-by-step how a 34-channeled brain-machine interface is microfabricated on top of a silicon wafer. Let's walk through this step-by-step. Starting at subfigure A, the process begins with a clean silicon wafer. So what is a silicon wafer? Well, silicon is an element, atomic number 14. The wafer is a thin, polished disk of silicon crystal in a diamond lattice. The diamond lattice of this crystal has powerful chemical bonds and tends to be flat and uniform. In other words, silicon crystal is smooth and tough at the scales of size and force and heat that matter for microfabrication. This consistent crystalline lattice of the silicon acts as an even surface on which to add other layers of materials during microfabrication. In order to make the surface of this disk a uniform surface that's also capable of forming weak bonds with the next layer of material that's layered on top of it, a layer of silicon dioxide needs to be quote-unquote grown on the surface by baking the silicon disk in an oxygen-rich chamber so that the oxygen binds to the exposed silicon. The oxygen molecules in the resulting SiO2 layer can then form hydrogen bonds with the polyamide. Once a layer of SiO2 is formed, it can be flattened into a smooth surface by chemical and mechanical polishing, and now the next layer of material is ready to be added. In order to put a uniform thin layer of polyamide on the disk, the silicon disk has to be put onto a vacuum chuck, and then a polyamic acid solution, which is composed of the precursor to polyamide and some kind of solvent, is then deposited onto the spinning disk. And the forces of its spinning pull the solution across the wafer, where a thin layer of the polyamic solution can adhere to the SiO2 via weak chemical bonds as the solvent evaporates. After the solvent is evaporated, the disc undergoes a process called a hard bake, which converts the polyamic acids into polyamides and cures them into a cross-linked final product. The next step is to expose and develop a template design onto the photosensitive polyamide. Remember, photosensitive just means that hitting it with light makes it vulnerable to a solvent or invulnerable to a solvent, depending on the nature of the photosensitivity. So the template that's projected is going to make a design for the ultimate final product of what stays on the disc and what washes away. A template of shadow and light is projected onto the photosensitive layer, so some of the polyamide will remain in place when exposed to a solvent, and some of it will simply dissolve. You can see the valley in this structure, and that is the shape into which gold will be deposited. So the next step is adding a layer of gold via sputtering. But what exactly is sputtering? Sputtering is the process of bombarding a sheet of gold with ionized gases in a vacuum chamber to knock the gold molecules free so that they shoot onto the polyamide. The net result is a fine, thin layer of gold atoms deposited onto the polyamide layer. The next step is to again apply a layer of photoresist. This is analogous to how the polyamic acid was applied and polymerized earlier, except the photoresist isn't a functional part of the finished product. Its only goal in this whole process, its whole life, is to act as a template for the next functional layer of material. Photoresist solution is spun onto the disc while being softly baked to evaporate the solvent, and then is exposed to light in a masked template, which can be then developed chemically so that the template design is remaining on the disc and the rest of it washes away. In this case, the negative space of the photoresist layer, the part of the photoresist which was not cured, washes away. And that space is actually exposed gold. This exposed gold, unprotected by photoresist, can then be etched away by a wet etching process in which chemicals wash away any portion of the gold not protected by photoresist, or by dry etching process, which is like sputtering in reverse, where argon ions are shot at the disc to knock away the gold. So to recap what's happened here, a bunch of gold was layered down, and then a protective template was put on top of that gold so that the rest of the gold could be destroyed and removed from the disc while preserving some of the gold in a specific pattern. After this, another layer of polyamide is applied, patterned, and removed where the gold contact is needed with a circuit board. So the finished design it's like a sandwich of polyamide, gold, and then polyamide again. It's a pattern of conductive gold circuits encased in an insulation layer. Now, the finished structure can be removed from the silicon disc. The gold is exposed at one end, ready to connect to the bus of a chipboard. Okay, that's a lot of techniques, but we've gone through it once, and so those are the basic steps involved for layering down microfabricated gold electrodes and insulating them. The specific ways Neuralink did their fabrication are more advanced, and they're, again, not entirely clear in the paper. So I had to do a bit of digging and make some guesses about how they're likely doing things. So in the paper, they just write, quote unquote, other microfabrication techniques are used. And that means that I can point to similar microfabrication goals being achieved with this or that technique, and that might be appropriate or used in that paper, but without an explicit explanation from Neuralink, we're just guessing here. With that, let's move on to a detailed example of thread construction from the academic paper, which was cited in the Neuralink paper. The paper includes a detailed explanation of a similar design process in section 2. The microfabricated design for the electron thread is shown in figure 3, which is here on the screen now. Let's go over this fabrication process in detail. As in the first example, this process starts with a disk of silicon crystal, which is then treated to grow a layer of silicon oxide, onto which a polyamic layer is spun and then cured into a polyamide. The next step is to apply a layer of photoresist and make it into a template by using light and chemical treatments as discussed earlier. After that template exists, evaporated platinum is deposited. This is different than sputtering, as no ion bombardment is needed to make loose platinum ions. The process is also called vapor deposition, which is a way of depositing thin film of metals by holding both the silicon platform and a section of platinum in a vacuum, and then just heating the platinum until it begins to shed atoms, which then radiate out in the vacuum, where the silicon disk has been set to collect an even film of the radiating platinum. I'll have a video at the end of this if you want to learn more. In other words, platinum is heated up until the atoms begin to evaporate into the vacuum. They move in a straight line until they hit their target. Platinum is usually bound to the polyamide layer via an intermediate adhesion layer. The result is a layer of platinum on parts of the polyamide that are not protected by photoresist. Once a thin layer of platinum has been applied, the remaining cured photoresist can be stripped away with liquid chemical remover or plasma bombardment. Why are we talking about platinum? Well, because in this diagram and in this pilot prototype, platinum was used as a conductor instead of gold. Neuralink would later switch to gold as a conductor, but the thought process is similar. So you can assume that Neuralink is using gold sputtering or gold evaporation instead of the platinum evaporation process here. As in the first example, after the metal is deposited down and the excess is removed, another layer of polyamide is applied and then cured. Next, another mask layer is applied. This time it's actually made of silicon dioxide. So silicon dioxide is used instead of regular photoresist because it serves as a hard mask, meaning it's resistant to etching techniques that would otherwise cut through a softer mask layer. Importantly, it can also be precisely etched itself. So the mask of silicon dioxide will precisely protect the polyamide underlying it. The silicon dioxide layer is applied via electron cyclotron resonance. In this figure, this is referred to as plasma-enhanced chemical vapor deposition. What a mouthful. This process, as I understand it, works by pumping gaseous forms of silicon and oxygen into a vacuum chamber and then energizing these precursors by generating magnetic fields which ionize the gases into a plasma, rather than using a high temperature or ion bombardment. When the electrons of these precursors are at such a high energy state, they become very reactive and form unionized solid silicon dioxide molecules, which are then deposited onto the disk. Again, there's a video description of this process at the end of this video. The silicon is then patterned into a mask via a new kind of etching technique. So this isn't photolithography. This is called reactive ion etching. In reactive ion etching, compounds, usually of chlorine or fluorine, are pumped into a vacuum chamber and made into a plasma of reactive ions via radio wave heating. When the reactive plasma hits the silicon dioxide, it chemically reacts and forms reactive products that are easily removed by a chemical wash. The next step is to etch the polyamide using an etchant that attacks the polyamide, but not the SiO2. This would leave polyamide in the areas where the SiO2 is protecting it, which creates the pattern in polyamide that you want. The term hard mask is used to distinguish these types of masks from soft masks, which are typically made of photoresist. Hard masks like silicon dioxide can withstand more aggressive etching conditions and offer better control over the etching process compared to a soft mask. This makes it suitable for processes that require high precision or where a substrate might be exposed to prolonged and repeated etching steps. The next step is to add a copper electrical bus for a future electrical plating step. This one's a bit tricky to understand, but the basic picture is that in order to make a connection with a later metal structure, they first have to have a layer of copper on which the other metal can be bound. This is because the future process, which is called electroplating, involves inducing the metal ions in a current that causes them to adhere to the copper. So at this point, copper is evaporated onto the board, as we discussed earlier with other metals, and then etched into the correct shape, which is needed for it to function as an electrical bus. This is done by applying another mask template and then soaking it in an iron chloride solution, which dissolves any of the unmasked parts of the copper it comes in contact with. By looking at another figure in the paper, we actually see that the copper bus is not applied to the whole length of the thread. The Distal ends of each thread, which go into the animal, do not get copper buses. Only the proximal portion of the thread bundles, which need to be put into electrical contact with the PCB, are covered with copper at this point. Okay, the next step is to deposit and shape a thin protective barrier around those existing structures. A polymer called parylene is used. Unlike polyamide, which requires spin deposition, parylene can be deposited using evaporation. It's less of a flexible polymer and doesn't have as much heat and chemical resistance as the polyamides, but it does protect against moisture damage. The parylene is evaporated onto the board, followed by patterning an aluminum hard mask on top of it. The sections of the parylene that are unprotected by aluminum are then removed using oxygen plasma. Now, the section of copper which was applied earlier can be used as a cathode to electroplate nickel. Electroplating is a process where an ion, in this case Ni2+, is deposited onto another surface which holds an attractive electrical charge, in this case the cathode copper. The nickel is dissolved in electrolyte solution, and the thread board is then submerged into this electrolyte solution. Then a current is run through the copper and electrolyte solution, which drives the nickel ions toward the copper buses. This causes a small lump of nickel to form on the end of each thread. This whole stack of materials, which is now the finished thread, is then released from the silicon wafer and laid upon the PCB. The nickel lump serves as a wire bond, where the current conducted through the platinum thread will be transferred to a gold wire that runs to the PCB. In the end, big picture, this is a thread. A platinum trace embedded in a polyamide insulator runs to the far end, which goes into the brain, and has a tiny area without electrical insulation so as to be able to carry current from the brain. And that current travels to the proximal end, the part that carries the current from the platinum trace to the gold wire, which is connected to the circuit board. Okay, and remember, this whole process is being done so that a single thread has several electrodes in them. Now, in the case of the Neuralink design, they do not use deposited nickel and have a second wire of gold that they connect to the platinum trace. Rather, they use flip chip bonding to make contact between the threads and the circuit board of the link. A tiny ball of soldered metal is deposited directly onto the circuit board for each point of thread contact. So one tiny ball of metal for each channel. And then the proximal side of the fabricated threads can be precisely placed onto that grid arrangement of soldering metal. This is a more direct connection between the circuit board and the thread arrangement and replaces the wire plus nickel solution that was outlined in the 2019 paper we went over. Neuralink doesn't specify exactly how this is done, but the general process of flip chip bonding is to melt the soldering metal and connect microfabricated devices, like the electrode channels from the threads in this case, to another metal on a board using sound waves. Okay, whereas the papers above explain the exact sequence of microfabrication techniques used for designing electrodes and for designing threads, Neuralink's white paper skips over the specifics but goes into more detail on the architecture of the threads themselves. They apparently have over 20 designs for these threads. Some of them have barbs so that they grab the brain tissue after insertion. Some are thick, some are thin. They are all kinds of different styles. One specific detail Neuralink has revealed is that they've been experimenting with adding a coating layer above the exposed portion of the gold electrode. The function of this layer would be to increase the surface area and total conductivity of this exposed region that's in contact with the brain. They do list several chemical solutions for this, which you can find in the paper. So that's how Neuralink builds their little electrodes. Well, it's similar to how Neuralink builds their little electrodes. Just remember, this paper is old, and they have definitely changed the materials and manufacturing methods drastically since the original Neuralink prototype. That said, the final microfabricated array for Neuralink in 2022 at least looks like this. This is a picture of the microfabricated threads for 12 different Neuralinks, probably of 1,024 channels, assuming 4 by 256 channel architecture per unit. The red arrow points toward the proximal end of the link, where the threads interface with the rest of the Neuralink hardware stack, and the blue arrow points toward the distal end of the link, where the threads are inserted into the brain tissue. Finally, here is a relevant section from the 2019 paper describing the threads of the Neuralink prototype. I hope you can now read this and imagine in your mind what kind of objects these threads are. We have designed and manufactured over 20 different thread electrode types in our arrays. 2 example designs are shown in Figure 1A and B. Probes are designed either with the reference electrodes on separate threads or on the same threads as the recording electrodes. We have fabricated threads ranging from 5 micrometers to 50 micrometers in width that incorporate recording sites of several geometries. Thread thickness is nominally 4 to 6 micrometers, which includes up to 3 layers of insulation and 2 layers of conductor. Typical thread length is approximately 20 millimeters. To manage these long, thin threads prior to insertion, Parylene C is deposited onto the threads to form a film on which the threads remain attached until the surgical robot pulls them off. Each thread ends in a 16 by 50 micrometer square loop to accommodate needle threading. Okay, one more thing. It's a cool throwback. I actually met Dan, the primary investigator for the Neuralink Vision team, at Society for Neuroscience in 2022, and I got to hold a link. So here's a picture of us. He's holding the silicon disc of the microfabricated threads, and I am holding the link. That's all. Just thought that was cool and thought that I would share that too.